Hello and welcome to this second lecture of the lecture series on game theory called Let's Game It. I, Ronak Sil, along with my friend Uni Narayan, bring to you the second lecture of this lecture series. Hope you all have liked the first lecture and have followed that. With that hope and without any further ado, let us start the second lecture. Now, in the second lecture of today, we are going to learn about simultaneous move games. We'll start, not possibly start, but we'll touch upon a murder story from where we'll talk about the concept called Prisoner's Dilemma. Then we'll define the concept called a pure strategy Nash equilibria. Then we'll try to find out the different ways in which we can define a Nash equilibria or we can find a Nash equilibria from a matrix or Payoff Matrix. Then we'll go on to talk about the dominant strategies, best responses, unique versus multiple Nash. Then also talk about an interesting trivia about an mathematician, game theorist, engineer, whatever you name it, he has expertise in that. We'll talk about him. And then we'll talk about a handful of games, even though I have written a handful of games, but I'll be talking about only one particular game which will pave the way for the next lecture of ours. So that is the reason why I'm putting that, and then we'll talk about the summary. So with that, I hope the contents are clear. So just a note of caution before we start that I may not follow the strict the topics that have been mentioned in the contents. So broadly speaking, the topics that we're going to cover today are very much interlinked. So while talking about one particular topic, it may so happen that the other topic mentioned in this list might come over there and might get repeatedly come over in the next consecutive slides as well. So please bear with us because the topics are covered in that way, because the topics are so related that it becomes very difficult to segregate one completely, isolate one completely and talk about that. So for that, kindly bear with us. But majorly these are the topics that we're going to cover. Now let us start. So what do you mean by simultaneous move games? As the name suggests, that the games are said to have simultaneous moves if the players involved in the game move or take the action without the knowledge of what their rivals have chosen to do. And that's the exactly why it's called simultaneous. That when you're playing a game, whatever game it might be, the people with whom you're playing the game are not aware of the move that you're going to make. Neither you are aware of the moves that are going to be made by the opponents of their game. Now, a game can be a simultaneous game even when the players choose their actions in isolation, with no information whatsoever about what the other players have done or will do. Now, to give an example, see, there are the various producers of, let's say, the television sets, or the studios, or so automobiles, or any other product for the matter, make decisions about their product design and features without knowing what rival firms are doing about their own products. Now, it may seem a bit unrealistic. You may say that it need not happen. So, yes, I understand it need not happen. So always, there are of course some kind of information leakages that happen in an industry like that or in any kind of setup. But for the time being, we are keeping all those things aside, and we are only focusing upon the situations where the players who are involved in the game do not have any information whatsoever about the moves that are going to be made by the opponent players. Now the question arises, then how can the other players make a move? Should they make a move based on their guts, or should they make a move based on their the historical performances of their opponents? Now that is what is the intriguing factor of a simultaneous move games. We're going to talk about that. Keep that, hold that thought. We're going to talk about that in the consecutive slides. But let us first brush up the concepts of payoff matrix that we discussed in the last slide. If you remember that this was how the payoff matrix was looking like, and this is the person 1 and this is the person 2, and this is their action profile, and this is the action profile of person 1. So how do you find an equilibrium? Last time we talked about how to define a payoff matrix like this. Now today we're going to talk about how do you check whether there exists an equilibrium, and what do you mean by an equilibrium over here. So just assume that you are person 1, okay, and given the person 2 chooses action C. As you can see, action C over here, action C. You are person 1, okay, person 2 is choosing action C. What is person 1's best response? So what do you mean by that? If person 2 is choosing C and he's getting payoff 2, and you by choosing action A are getting 10, but if you choose action B you'll get 12. So you will choose B over A, given that person 2 has already chosen action C. Now you should underline the best payout given the choice of the other player. Now given person 2 has chosen a particular strategy, you need to choose the best strategy available to you. Now choose action B, as we have mentioned, since the payoff from that is higher, 12 is greater than 10, so you can underline that. Now assume that person 2 chooses action D. Previously he was choosing action C. Now if he chooses action D, he gets 3 and 1. So the comparison for the column player should be row wise. In this particular case it is a column wise, in a sense. See here, let's say the person 2 has already chosen action D. Now depending upon what the person 1 is choosing, his payoffs are going to be determined. So let's say if person 1 is choosing action A, he is going to get 8 and the person 2 is going to get 3, otherwise 10 or 1. So given the person 2 has chosen D, what is the best response of the person 1? It should clearly be B, because he is getting higher payoff. 10 is higher than 8. So you can underline that. Now similarly you can keep doing this. Now assume that you are person 2 and do the similar process, repeat the similar process for person 2, assuming that person 1 is choosing A and B, and find out the best responses and underline them. After doing that, you discover that the boxes which have both the numbers underlined are considered to be the equilibrium, or in this case 12 and comma 4. That means for person 1 it is action B, for person 2 is action C. B C or CB, whichever you want to call it, 12,4 is the equilibrium in this particular case. This is one of the many ways of finding out an equilibrium, or what we should call it as a Nash equilibrium, because it is named after the famous mathematician John Nash. That's how we find a equilibrium. Now let us formally define what is Nash equilibrium. So a Nash equilibrium in a game is actually a list of strategies, one for each player, as you have seen, such that no player can get better off by switching to some other strategy that is available to him or her, while the other players have already made their moves. That means, now just consider that if we move from this box to any other box. So let's say in this box person 1 is getting 12 and person 2 is getting 4. So let's say, when will person 2 move to next box? The person 2 will move to the next box only if he or she is getting higher payoff, but if he or she moves to next box, he is getting 1. So he or she will not move. What about person 1? He also will not move to the next box, that is this box, because he is getting higher payoff. So always remember, for the person 2, the column player, the comparison is this way, row wise, because the actions are this. But for the row player, the comparison will be column wise, because the actions are this. So the comparisons are between the actions, or the payoffs that you get from the actions. I hope this is clear. So that is formally, to state formally. So in this box, both of them maximize their utility or maximize their payoffs. In no other box you can see that they can maximize their payoffs. Means even if in any of the boxes this guy gets a higher payoff, it also depends on the strategy taken by person 2. So simultaneously, after they have played, this is the result or equilibrium situation or place that they arrive at. Now the question that we were talking about before, that if both of them are making simultaneous moves, how is it that the other persons will understand? Will they only make their moves based on beliefs? I have given the answer. Will they make their moves based on their guts, or will they make their move based on something else? One method, when you're playing a game with another person, is what you call the experience and observation. Let's say if the players play this game repeatedly over a period of time, or play similar games, or have been playing similar games, then the players would have a pretty good idea about the moves that the other players are going to take. That is one method. It's a very unique. It's a very common method. The other method is a logical process of thinking through the other's thinking. That means you put yourself in the shoes of the opponent and think what he or she might have done if, or what you would have done if you would have been in the shoes of that person. So you're thinking through being a person which you're not. But this process might be a bit tricky. If you don't know the person or don't know the opponent, then this particular process called the logical process of thinking through might not work. So what exactly drives the actions taken by, the strategies taken by the players over here? This is what the game theorists love to call as beliefs. So people have certain beliefs about the other players. The belief can be, let's say, in a particular neighborhood, you and your neighbors are playing a game, so you have observed your neighbors over the period of time, so you have a belief, you have a gut feeling. Maybe gut feeling is not the right word. You have a belief, or you think that this might be the strategy that the other person might be playing. Please do not use the words called forecast or any such statistical or econometric terms, because these are the terms which have a formal definition and they don't fit in this. It's not forecasting. It's rather saying something based on your beliefs. You have a certain belief system, and based on that you make a move, and that is what possibly drives the actions or justifies the actions to a certain extent taken by the players of this game, of a simultaneous move game. Now let us talk about a very interesting concept called a prisoner's dilemma. So we can just go through this entire thing. I'll just tell you in brief what's happening. So there has been a murder committed in a nearby place, let's say, and a couple has been convicted, or rather I should say the couple has been arrested with a charge that either of them or both of them have been involved in the murder. Now there are two detectives called Detectives Green and Lupo Place. They keep the prisoners in two separate rooms and tell them, that if they try to convince them, how the introduction goes. You go to Hollywood movies or web series or any typical Bollywood movies, how the introduction goes. Similar kind of interrogation is going on, where they have been taken to two separate rooms and they have been told that, if one of them confesses, then the charge or then the punishment will be lessened for that particular person, but only if the other person denies. The other way around. If one person confesses and the other person denies, then the person who is confessing is getting higher term of jail as compared to the other person. Now, if both of them confess, then they are saying that the total number of punishment, the total number of jail years can be brought down, but not as much as compared to a situation where both of them deny. If both of them are denying, that means they don't have any evidence to link them, and both of them can be set free, so both of them are innocent. So this is the situation. Now this is a payoff matrix. So husband has two things. Either he can confess or he can deny. Wife has two things or two strategies at her disposal. Either she can confess or she can deny. Now why it's called defect and cooperate written in the brackets in the parentheses? Why? Because if both of them confess, if both of them deny, that means both of them have had a premeditated plan that they must have committed the murder, but now they have, they don't have any grudge against each other. They don't want the other person to get the entire punishment. So they have decided it that when the police will ask them, they would cooperate, and they both of them will deny. And why confess is called defect? Because let's say both of them initially thought that they would deny, but now maybe the detectives will lured them with some rewards or something, and if one of them decides that that guy is going to confess or that guy is going to speak against the other person, then the other three situations might arise. If both of them confess that they have committed the murder, then 10 years of jail straight. If one of them confesses, let's say the husband confesses and the wife denies, then the person who is confessing is getting 1 year, the person who is denying is getting 25 years. Other way around for the wife. So see the danger is there. So if one of them, if they don't have a cooperation, proper cooperation, then they end up either in this box or in this box or in this box. Now just by using the method that we have used just now to find out Nash, if we find out over here, we'll see that there are two Nash equilibriums that are existing. So this is one and this is one. But clearly this one is much better, theoretically if you see, practically if you see. Because if both of them deny, they just have to go for a 3-year sentence. If both of them confess, they have to go for a 10 years term. Now, as we can see in the previous example, you have seen that there is only one pure strategy Nash equilibrium existing. But here we can see that there are multiple, that means two pure strategy Nash equilibrium are existing. We say that for the husband, the strategy confess is a dominant strategy, or the strategy deny is a dominated strategy. Why do we say so? Now see, from here we'll understand the concepts called dominant strategy and dominated strategy. Now let's say we have touched upon it, in the previous example. Now we are doing it formally. Now let's say the husband confesses irrespective of what the wife is going to do. So if the husband is confessing and wife is confessing, 10-10. If the husband is confessing, wife is denying, then husband is getting 1 year. Now just see over here. If he denies, in both the cases, whatever be the decision of wife, he is getting 25-year term and 3-year term. So clearly, if he confesses, irrespective of what the wife's decisions are, he is getting 10 and 1, which both are lesser than 25 and 3. So that means this is clearly the best strategy of the husband, irrespective of what the wife is deciding. Now, does a wife have a dominant strategy like that? And this confess is called a dominant strategy for the husband. Similarly, if you apply the same logic, you'll see for the wife also, the dominant strategy is confess. So you add both the dominant strategies, you arrive at this particular equilibrium. Now that's where the dilemma is. In a prison's dilemma, even though if they cooperate, they'll end up here, which is a far better outcome, they would not, and they'll end up by using the concept of best strategy or best response that we have discussed just now, they'll end up at a worse outcome. Had they cooperated, they would have ended up here, but that's where the dilemma comes in, and that's why it's called a prisoner's dilemma. Now over here you have seen that there is a dominant and dominated strategy that exists. What if there is no dominant or dominant strategy? Then what is the way of finding a Nash equilibrium? That's where the best response analysis comes in. Now this is a normal game. Let's say there's a row player and there's a column player, and for the row player, these are the 4 strategies available: top, high, low, bottom. And for the column player, these are 3 strategies available. These are the payoff matrices. Now, in this particular, by using the strategy that we have used here, which is the strategy of dominated or dominant strategy, we will not use that here, because if you use it over here, you will see that there is a dominant strategy for either row or column player. Then how to find out Nash? The best way to find out Nash in this kind of case is called a best response analysis. So what you are going to do is, you will take each strategy of row player and column player separately. So take the row player first. For row player, if he plays top, or let's say, okay, we'll do it this way. Okay, so let's say the column player has played left. Then there are 4 options the row player can play: either top, high, low, or bottom. Now he'll see which one is giving him the maximum payoff, given that the column player has played left. So to the strategy taken by column player, what is the best response of row? Which is clearly 5. You see, 3, 4, 2 and 5. Amongst this, 5 is the highest. Similarly for middle, if the column player is playing middle, what is the best response of row? Top, high, low, or bottom? There are 2 best responses, low and bottom, because both are giving him 5. Similarly for this. And similarly, if the row player is being top, what should the column player play? Left, middle, or right? Clearly middle, because that is giving him or her the maximum outcome. So in this way, if you eliminate, this is what you'll arrive at. So this is the Nash equilibrium in this particular case. So in this way, you can find out if there is a unique Nash or there are multiple Nash, or it might so happen that there are no Nash equilibriums at all. Now, before we move ahead, let's talk about this trivia. This person is very famous. He's called Professor Derek Abbott. He's pioneer in the field of what is famously known as the quantum game theory. We always think about game theory to be a tool used by economists or mathematicians, or maybe the people who are working or doing research in the field of management. But this person, he has pioneered a field called quantum game theory. What he does is, he is actually an engineer by profession. So he uses quantum mechanics, or he uses, rather the other way around, he uses game theory and quantum mechanics together. So he uses game theory in quantum realm. So this is a very nice example of where there is a bridge that is being the gap between 2 different kind of subjects being bridged by this pioneer called Professor Derek Abbott, who is using game theory in the field of quantum mechanics, or the other way around, you can say the quantum mechanics in the field of game theory. It's very interesting. You can read that he has published several papers and has had authored 1 or 2 books as well. Now we'll discuss the last game, which is called the chicken game. What do you mean by chicken game? Chicken game has few essential features for any particular game to be a chicken game. What? Each player has one strategy called tough strategy, other strategy called weak strategy. Now each player strictly prefers that equilibrium in which the other player chooses chicken or weak. Now the payoffs when both players are tough are very bad for both players. Now think of it in this way. Let's say you and your friend, both of them would like to race, or would like to play some bold games. In that particular case, you might decide that you both are going to run a race in a very dangerous place, let's say on the railway tracks or near the railway tracks, and the ending destination is going to be the railway tracks. I'm going to give the typical movie examples that you can see in Bollywood or Hollywood. Why it's called a chicken game is, let's say two friends are going to cross a rail line, that being their destination, or that being the destination of the race, or the other way around. Let's say both of them are moving or racing towards each other, and they say that whoever is shirking first, or whoever is swerving first, or whoever is stopping first, is going to be considered as a chicken, and whoever is going to go through is to be considered as the winner. But now think of a situation where both of them swerve, or both of them stop. Then both of them are opting for what we call the weak strategy. Then both of them can be considered as chickens. Now, if one of them stops and the other person goes, then the other person who did not stop is going to be considered to be the winner, and the one who stopped is going to be considered to be the chicken. But the worst possible outcome is when both of them, feel bold and tough and want to collide with each other, and they don't stop. They want to be bold, and that's where they meet an accident. So this is a typical game. You can think on the lines of what I have discussed just now. So either both of them can swerve, or in that particular case they'll give a chicken. But in this case, when both of them are going straight at each other, being tough and bold, they're ending up at a worse outcome. And if you see whether there exists a Nash equilibrium or not, you'll see there is possibly no Nash equilibrium that might be existing in this particular case, because whichever strategy box you take, there's always a better outcome for the other player. So we have seen that there are games where there is one pure strategy Nash, but there are games where there are multiple pure strategy Nash. Sometimes there are no pure strategy Nash that are existing. Then isn't there any other way out if there are no pure strategy Nash? Yes, there is, and that is what is called mixed strategy Nash, and that is what possibly we might take up in the third or maybe in the fourth lecture. For the time being, just hold that thought of mixed strategy Nash equilibria. We'll be discussing it in our consecutive lectures. Now, to summarize, basically we've talked about the simultaneous move games. What do you mean by that, or the definition of that? Then we've introduced the concept of Nash equilibrium, different ways to find a Nash equilibrium, and finally we have talked about multiple Nash and no pure strategy Nash, and what to do in those situations is going to be discussed in the next or in the consecutive lectures. Now, to be frank, that was all from my side. Today the lecture went a little far. I'm really sorry, because we have to squeeze so many topics in the few lectures, so that's why it might have crossed. So I'm really sorry for that. I hope you have enjoyed this, and the references for this particular lecture will be given in the consecutive lectures, because I'm trying to give all the references towards the end. But those who are interested, those who want to start off, they can start with the book by Avinash Dikshit called Games of Strategy. That's a very nice book for the beginners. So you start reading from that book, and most of the examples also I have taken from that book. So that will be a nice read. Read that, just go through it, and come for the next lecture. So hope to see you in the next lecture. Thank you.